Now, why is that important? Well, let's start with something a little simpler. If you have a spherical star, which is going to reside here, spherical star, sitting there, it's not rotating, because that makes it more complicated, and you have an orbit around the star, which is a perfect sphere. It's actually an ellipse, which is pretty good. But that makes it more complicated too. If you have a perfect sphere around a star, every point on that sphere, because it's drawn like a circle because we're looking at a cross section, every point, if it has the same distance from the star, has the same gravitational potential. So basically, if you're in that position, you can walk around and you're not losing any energy, right? If you're in space, you can orbit with that potential. It's exactly the same thing as if you were on like a hill and you're like, well, I'm tired. I'm too tired to walk up. I don't want to walk down yet. I'm just going to walk around in the same position because the comparison doesn't really work. We could talk about something like the view would always be the same. I don't know. It doesn't really matter. The point that I'm trying to make is that if you have a single star, there is a sphere around that star that has the same potential, which is fascinating. You can see this on the diagram. We have mass 1 and mass 2. This is when a laser pointer would have come in real handy. Why didn't I bring one? We have mass 1 and mass 2. You can see around both, closest to them is a circle. That's this circle, except they didn't draw theirs as nicely. That's a surface of equipotential. Now, I have one more diagram, just because I love it. And I'm so good at this. Okay. Imagine that you had a bizarre bucket. It's not like a normal bucket. It's a crazy shape. And you took a slice through it. And this bucket had a lip here. This is the lip. And then it went down, and it had a little dip here, and then it had a littler dip there. All right. There we go. I couldn't draw my own bucket. What would happen if you started pouring water into this bucket? Right? You started filling it up. Filling it up and up and up and up. At this point, here, something interesting happens. The state of the bucket changes. And that is because you still don't have enough water in it to overflow the bucket. Not by a long way. But you have enough energy. Sorry, did I say energy? I mean water. You have enough water to start filling up the other side. This is exactly the same thing that's happening in this diagram up here, except the diagram is looking down on the bucket. So mass 1 is our primary star. Mass 1 is our degenerate star. Mass 1 is our heaviest star, which has got this incredible force of gravity. It's got this incredible potential. And you can see that at a point, which is actually the Lagrange point for people who are studying for first year physics in the back, you actually get a position with these stars where the equipotential surfaces actually match up. What does that mean? That if you have mass in this side and this happens, that mass can then move to the other star, which is fascinating. So this is exactly why cataclysmic variables are so interesting. It's because they can actually steal the mass of other stars. Now, you don't look impressed. That's okay. Does that make sense? Yeah? Cool. Very good. The interesting thing is you still don't have enough energy of the material to have the material escape the system. All of the material is trapped in this binary system, but you do have enough energy to transfer the energy from the lowest mass object to the heaviest mass object, which is a fascinating thing. Now, this is a problem, and I know you're thinking, Andy, whoa, this doesn't work. are going to move apart. If the two objects move apart, Andy, the Roche slope isn't going to work. It's going to grow. It's going to be too big. You're going to need too much energy. This thing's going to stop. And that would be the case. But the fascinating thing is that not only do we have this transfer of mass, we have a subsequent transfer of angular momentum. So we actually have a process occurring that has to do with the magnetic field of a star, which is bringing these stars closer and closer together. So this process actually becomes more efficient with time, which is really neat. It overcomes the tendency of the system to separate and actually keeps these things going. Now, where were we with this? Got to the end of my notes. Now we're really in trouble. I've got another picture. Hopefully this will help. This is another way to visualize what I was just talking about. Okay, so you're thinking, right? You're thinking, okay, fine. You can move you can move mass from one star to another. That's fine. Why would you want to do that? What difference does it make? Well, it actually makes an incredible amount of difference, which is really interesting. And this is the last thing we're going to talk about tonight. The fascinating thing about this, you can come in, please. The fascinating thing about this is that if you start dumping mass onto this white dwarf, you start dumping mass onto the degenerate star, a lot of interesting stuff happens. That mass is bringing with it a lot of energy. And this is where the most energetic process in the universe comes in. This is the process of accretion. This is the process by which, if you have an object with gravity and stuff falls towards that object, it gives up a lot of potential energy, it gains kinetic energy. This is the most efficient way to harvest energy in the universe, which is amazing. And in an ideal situation, it's 20 times more efficient than fusion. It's better than stars, which is really cool. I think that's amazing. This is what I didn't know. I'm really excited about it. What does that matter? Well, so you've got all of this energy. Funnily enough, half of that energy is left in the accretion disk, because this is a little simplistic. As the material is being pulled from one star to the other, it forms an accretion disk because of transfer of angular momentum. I'm not going to go into it. It leaves half of its energy that it's gaining as it falls into the system. It leaves half of the energy in the disk, and then it impacts on the surface. Bam! Really, really hard, because a white dwarf is solid. You can't compress it because it's already degenerate, and this stuff is normal matter. So it hits it like a brick wall. And pretty much all of that energy is radiated away, which is good for us, because it means that these objects are really bright. Otherwise, we wouldn't be able to see them, which is really interesting. The more interesting thing, though, is that the mass that you transfer onto the surface of this degenerate white dwarf actually manages to compress it even further. And that's where you get the real dividends. That's where you get all of your gravitational energy. That's where you can heat up this object, which can be as cool as maybe 4,000 or 5,000 degrees before mass transfer begins. And you can heat it back up to 60,000 degrees Kelvin. This is really great, because now you start to see radiation from this object. You start to see these things, and that's really awesome, because like I said before, these are some of the most popular objects in terms of frequency. These are some of the most, what's the word I'm looking for? Common objects in the universe. And if they weren't doing this, we wouldn't see them, which is really interesting. Now, I know that I see it, that these things, that they live a long time. This situation can continue for billions of years. So these things basically become immortal. They've already lived 10 billion years, 15 billion years, depending on their mass. They can't continue this indefinitely, but they can live a very, very long time. These things are quite incredible.